Hi, twin. Good morning, twin, or good afternoon, twin, or good night, twin. This is going to be a Taylor series. The first lecture about this is just like explaining how the series works. The second lecture is how we can use. Wow, voice crack. That's crazy. Sorry. The second one is how we can use the Taylor series to like approximate integrals and stuff like that, and yeah, like use it to like find like the upper bound of like error. And then the third thing is just using Taylor series for like difficult derivatives. Like this one example, you can use like the hospital rule, but you have to use it like 6 different times or 5 different times, and that's gonna get like really messy with each derivative. So it's just easier to use the Taylor series. So yep, that's what this is gonna be about, twin. So lock in right now. Maybe I'll put like timestamps for the different lectures, or maybe not. Maybe I'll get lazy and I'll forget, and then you're just gonna have to do it yourself, twin. We'll see, twin. Okay, so Taylor series. You should probably know this equation, this one right here. But it's the sum of, and then we have c of n x minus a to the power of n. So we have x. A is the center, whatever the center is, and then n. And then, well, yeah, so that's their series. And then I think you've heard of Maclaurin series, whatever. And that is, it's slightly different. This is just basically if a equals 0, so if the center is 0. So if you plug in 0 right here, wow, that's so pretty, right here. So if you plug in 0, your new equation is going to look like this. I wrote that too high up. Okay, no, it's too late. So, oh, wow, it's been a while since I've done this. That's so beautiful. Okay, I don't know if you can, understand that. But that's a function, and then this n right here is the derivative. So, like, first derivative, second derivative, whatever. N is whatever derivative of 0, which is, because a is the Maclaurin. I'm just saying Maclaurin, okay? Maclaurin, think about it like this. We want Maclaurin to get DNS, we want it to get 0 points, so Maclaurin equals 0, okay? So, Maclaurin is when a equals 0, okay? So, in the Taylor series, like if you look right here, normally it's like f, the function of whatever n derivative, and then parentheses a over n factorial, right? But for Maclaurin series, a equals 0, so then we just plug it in here, which you can see. So that's what Maclaurin series is going to look like, right? So that's the two, I guess like 3 equations you should know, 2 equations you should know. Jumping into it, okay? I think we skip this one. Okay, so they will give you the sheet right here that lists out the common Maclaurin series, because like each one over here has like a corresponding series, right? And then the corresponding interval of convergence, right? So these are like the most common ones, most simple ones. So you don't have to memorize this. They will give this to you, but I will work out like one of them just to show you how like they got this basically. So I'll write in blue. So question: find the Maclaurin series for f x equals cosine x. What is the interval of convergence for the series? Okay, so immediately it says Maclaurin series, so we know that a is equal to 0, right? And then Maclaurin series, right? The equation from up here, so we can write that. I'll write that right here. So fx is going to equal the summation. Let me write this bullshit of f and then n derivative 0 over n factorial times x. And boom. So, right. This is what we have, right? So, when we're starting out like this, and because usually there's like 2 different ways to go about like these equations, right? So like the first way is make a chart. Wow, make a chart. Beautiful. And the second one is like build off one of these, right? Like sometimes, for example, if you have like sine and you have like x squared instead of like starting from like scratch and making a chart for all of it, you could just use this one instead, right? The common Maclaurin series that they give you and like tweak it a little bit. But since we're starting from the beginning, we don't have this chart, right? So we're gonna start from the top basically. That's what I'm saying. Twin and M. Okay, so you're gonna make the chart. First one is n, and then the second one, just for your convenience, it's gonna be f 0, and then oh no, it's not. I just lied to you, twin. That was a test and you failed it. If you didn't catch that mistake. Okay. And then the next one, n derivative of 0, because we're trying to yeah, I'll just write it out. We're trying to get to the final thing, which is going to be this. Right? This is what we want, right? Because we're trying to get to this thing, right? So in order to do that, we break down each step. So we find n first, and then the f like derivative of just x, and then we plug in 0 next step, and then we plug it into the final, right? So that's the step-by-step process. So we're just going to make a little chart here. Okay, beautiful. Ooh, that's not a straight line. Okay, perfect. I hope that's enough space. I'm writing blue. So usually for these, they don't say it. If they don't say it, I just assume it's n equals 0. Okay, right? So usually going up to 4 is enough. Sometimes less, sometimes more, but like it's dependent on whatever. Wow, so this is not long enough. We just make this line a little bit longer. Perfect. Okay. Okay, so okay, so this is our wow f of x, right? It's cosine x. So starting with the first one. So when n equals 0, that means like just the original, right? So we just write cosine x right here, right? And we keep x, right? We're not plugging any numbers in here. We're just looking at it face value. Where this column derivatives of the expression, and then the next one is derivatives plus plugging it in, and then the last column is just plugging into the last thing, right? So just in case there's any confusion. So 0 derivative doesn't roll, right? So n equals 1. That's going to be f of x to the first derivative. So what's cosine x to the first derivative? This is a test. 3, 2, 1. Okay, I'm going to hope you said negative sine x. That's the correct answer. Second derivative, do this with me, so I know you're not falling asleep, twin. JK, twin, you would never fall asleep. They're locked in, twin. And then n equals 4. Fourth derivative is going to be cosine x. And for example, here you can stop because it's a pattern, right? So we got cosine x again, which means the next one's going to be negative sine x, so we don't have to keep going. But that also means that n, whatever n is, we have no clue. So there's going to be a big question mark right there. So now we plug in 0, right? And then so we plug in 0 to whatever this is, right? The next one over. That's why we have like a chart to make it easy. Dummy. So cosine of 0, what is that? Hope you said 1. Okay. Negative sign to the 0. That's 0. Negative sign, yeah, right. So hopefully this is what you got, okay? And when you're doing this, if in this third column it's 0, you can just cross it out. Like that means there's no value, so we can't do anything with this. Wow. You get the points, because it's supposed to be crossing out. So if we continued the chart, the next one here would be crossed out, right? Okay, so then that means we're only looking at like the even numbers basically. So we plug it into this. So we already know what this top part of the thing is, right? So that's gonna be 1. Our n here is gonna be whatever n is. So in the case it's 0 factorial, and then x, and then whatever n is again. So that's gonna be 0. So then do that little fact that you should know, because I don't think you know this. Twin. 0 factorial is 1. Okay, so this case 1 times x to the power n thing is just 1, right? So this one's just 1. Okay, next one. Got the top again, right? So that's going to be negative 1 over 2 factorial times x to the n power, which is going to be 2, right? So now we have, I'm just going to leave it like that actually. We could simplify it later. The next in line, now we have 1, use from over here, bring it down, and then n factorial, so in this case it's going to be 4 factorial times x to the n, which is going to be x to the 4th power, okay? So, and then it keeps on going, right? So say we did the next one, that would be negative 1, because that's the pattern, right? It's alternating, and then 6 factorial times x to the 6th power. So we could go forever and ever, right? But basically, now we're like expanding it, right? So now we could also write that cosine x is equal to all of this, right? So we got 1 minus 1 over 2 factorial times x to the 2nd power. And then next term right here, wow, this is marginally better, bigger than the other term. That's okay. Right, and then it's going to go on forever and ever, right? So then for this, we make up, it's like a series that represents this. Remember how like in past lectures, it would be easier, but we find something that like represents this. So basically, oh, I just activated my series somehow. Hey, you can go away now. Thanks. So well, you're going to have this, right? So you can just write that down if you're lost. So if you're lost, we go step by step, right? So first thing, is it alternating or not? So if it's not alternating, you don't have to worry about it. But in this case, it is alternating. So we know for a fact that it's going to have something like this or something like n plus 1, just depending, right? I have no clue right now because I'm just looking at face value. I'm going step by step, so I'm just going to start with this, okay? Next, let's see. Well, how are we getting, like, I guess our numerator in this case? So our numerator is going to have some kind of x term, right? And then the powers are changing, right? But there's no coefficients, so the coefficient's always going to be 1 in this case, but the power is changing. So when it's changing from here to here to here, we see it's increasing by powers of 2, right? So just like guessing, it's going to be 2n, right? And then over our denominator. So in this case, it's like 2 factorial, 4 factorial, 6 factorial, right? So it's also increasing by powers of 2. So I'm going to have a feeling it's going to be 2n times a factorial, right? And then we can fact check this. So in this case, it's going to be, well, this is n equals 0, right? This is when it's, right? This term is when it's n equals 0. The next term is when it's, well, I guess in this case it would be n equals 1. Because it's, yeah, no, you get it, it's world 1. So this is what, so like plug in here, okay, so I'm just yapping and I'm saying a bunch of nothing, bro. So basically if we plug in the n's, we hopefully get our equation thing. So say we plug in 0, so we have negative 1, 0, and then x 2 times 0 is just 0 here. Wow, it's beautiful. And then 0 factorial, right? So then, well, negative 1, 0 is just 1 times x is 0 is just 1, right? And then 0 factorial is 1. So this one checks out. Try the next one. So we got negative 1, well, the n is 1 here, right? And then x 2 times 1 is just 2, right? And then bottom is 2 times 1 factorial, so that's just 2 factorial. And does that check out? Yes, that does. And once you've like checked the first two, it like should work, right? So I give you a chance to look at that. I'm gonna erase it because I'm running out of space. Because I write big as fuck on a fucking computer. Okay, so you might be thinking, are we done yet? No, fuck no. This is just like, yeah, this is step 1. Okay, step 2 is finding the this is finding the Maclaurin series right here. Is this thing right here, here, and then next step is going to be what is the interval of convergence, right? So I'm gonna guess you know what it is, but just in case, like say this is our thing, this is our sensor, right? This this whole thing is the interval of convergence, and in order to find that, we find the radius of convergence first. So right, so like say if the radius of convergence was infinity, then over here would be negative infinity, and over here would be just infinity. But if it was like 1/3, then the one over here would be negative 1/3, and over here would be just 1/3. And this is assuming that the center is 0, right? So it's a little breakdown. So next step is finding the interval of convergence. So in order to find that, we have to find the radius of convergence, right? So this is step 2. So how are you doing that? Well, we're going to use this, right? And we're going to use, okay, look at that. And then what test do you think we can use to find whether or not if this converges or not? Okay, I'm giving you 3 seconds to think about it. What test? What series? What test do we know that we have learned that you can apply to this? All right, 3, 2, 1. Hopefully you said ratio test. Okay, I have no clue if you did because this is a YouTube video. So, but I'm gonna guess. I'm gonna hope. And that says ratio test. Trust. Okay, ratio test. Right. So in case you forgot, ratio test is just the wow, a sub n plus 1 over a sub n, right? And then yeah, whatever. You know it. Yeah, you know it. I trust you, twin. So and we're looking at this. So wow. Well, remember, it's going to be absolute value, so we could just ignore the alternating sign thing. So now we have x 2n plus 1, right? But I'm going to write it out. So 2n, and then it's 2 times n plus 1, right? So that's, if you, what's it called? Not factor it out the other way. It's going to be 2n plus 2 right here. Wow, I should have scooted down a little bit, but it's too late. Anyways, plug in n plus 1 right here. You're going to get 2n plus 2 factorial, and then you just the opposite. So that's going to be from here to there, and then you just put this back here. So, right. So, and we know that it expands, right? So, because we're trying to simplify this shit, right? So this numerator right here expands. So I have no space. That's I guess I could write it right here. Expand it. So we have x2n times x2, because that's how that works. Remember, twin. And then this, which is 2n factorial. And then down here, we just bring this, and then we can expand the other one, which it's factorial, so we just write it all out. And going down one by one until we get what we want, which is perfect, right there. So we cross it out this, cross out this, cross out this, and then we're left with, well, I should have written, L equals lim, and approaching 0. You should write that in front of this, because it is the ratio test, and it might be on the like FRQ stuff, and you don't want to get any points taken away for being stupid, right? Don't be stupid. So write it right here. Wow, beautiful. That's a 0, by the way. Okay, so then we write what we have left over, so we have x squared over 2n plus 2 times 2n plus 1. Wow, beautiful, right? And remember ratio test, so we're testing this when it's approaching 0. You can take out the x, right, because that's like a constant, it's never going to move. So we bring that outside. Wow, no, that's beautiful. And then we have 2n plus 2, and 2n plus 1, right? So, and approaching 0, you put 0 into this, right? And remember, I just lied to you, it's n approaching infinity. So infinity on the bottom, that's going to be 1 over infinity, and we know that's 0, right? So this is going to be equal to 0, and then that's greater than 1. So according to the ratio rule, this converges, right? And now we kind of see, like, where, like, if there's any exceptions, but in this case, like, if there's any exceptions for x, right? So, but in this case, there is none, because whatever you plug into 0, into x right here, it's times 0, right? So that's always going to be 0, so that means it always is going to be under 1, so it's always going to converge. So that means this thing converges for all x, okay? So that's important. You should always check that, because it might be different, it might not be, but just for the safe side, right? So then, because we know that for all of x, it converges, our radius of convergence equals infinity, right? Because there's no exceptions, it doesn't stop anywhere. Thus, our interval of convergence is going to be negative infinity to infinity, and wow, and that's the answer. Yeah, no, this is taking like a little bit longer than I kind of expected, so I might break it up and I might not, or I might not. I don't know. I don't fucking know. Okay, I'm still recording. Okay. Anyways, common Maclaurin series. So yeah, you see, this is what we just did for cosine x, right? So it's right here, and you could fact check it. That looks exactly like that, right? So we just got that. Okay. And then so now we're gonna do like another example, but these are different. You see, like 5x, 5 to the x power, it's not here, right? Oh shit, right? For example, for this one, assign to x squared, not here, right? So what do? The first thing we do is cry, probably. It's around the test and we're panicking. But the second one is we lock in, because we're remembering, okay, if I don't have this exactly, there's something similar, right? So 5x, right? I'm going to give you a second to think about what looks like this. Which McLaren series should we use, okay? 5, 4, 3, 2, 1. If you said this one right here, you would be correct, okay? That's the series we're going to be using, because it looks similar, right? Dumbass. Okay, sorry, I didn't mean to talk you there. Right, so recall this, right? We're going to use these, and teacher said that we will be given this, so we don't need to memorize it. So if he's lying to us, then we're fucked. So hopefully not. And then don't forget the interval convergence. You should memorize it. So that's just saying like for all x c's, it's right infinity x infinity, right? Okay, so how do we make 5 of x look like e of x, right? Well, don't don't kill me, twin. Okay, I am the messenger here. But yeah, I write it right here. 5x, right? So how are we gonna get this to look like in this form, right? Because we're trying to make it, in this case, like in like the teacher's term, it's e, and then like the x is a something right now, right? So we're trying to find this something right now. So we need to put this in terms of e. So we need this, like, I guess like that, right? We need to put it in terms of e, right? So how do I do that? Oh, let me see. Here, I'll put it in blue. See. It's because like 5x is also going to be equal to e to the power of ln 5x, right? Because we can't like change the value, and then if you, but like these cancel out, so it's gonna, these equal the same thing. Is basically what I'm trying to say. Okay, I'm like stumbling with my words. Not my fault, Win. Okay, I'm not a calc teacher. Okay, but this is what we have, right? And this is in our e form. I'll do it yellow. So now this is our new something, or our new x, basically, right? You can also rewrite it to make it a little bit easier to look at, just like x ln 5. Wow, because you remember that rule for these things, you take out the exponent, and it becomes a new coefficient, right? So now basically this is going to be our new x, and this is going to equal our something, or our new x, basically. So I'll write it in this. Okay, I'm going to assume that Bing was not for me and not telling me to shut up. Okay, but basically, all right, this is our new x, and we're going to put it in this x to replace, okay, in this x, okay, because this is our known McLaren series, okay, and we're trying to make a new one for 5 to the x power, okay, so I'll do it red. Fuck it, I'll do it red. So, well, you can't really read that, so we plug in our new x to this equation, right? So our x is this, x and 5, right? And then don't forget the power to n over n factorial. Okay. And then I guess you could like simplify it out a little bit, make it prettier to look at. So then distribute the n. We got x n power times ln 5 to the n power over n factorial. And then yeah, that would be the answer right here, McLaren series, because it's just asking us to find the series on the interval of convergence. And when we're doing stuff like this, like using a previous like McLaren series, like 99% of the time, the bounds would be the same, or the interval convergence would be the same. So in this case, it is the same. So radius is going to equal infinity, so thus the interval convergence is going to equal the same thing as this, which is just negative infinity to infinity. Boom, that's the answer right here. Right? So simple enough, right? I'll do another example. You got this one? Fuck, this is not a live stream. I'll just quickly do it, just in case you don't got it to win. And it's a different example. So, find the McLaren series for this expression, right? So we know what sine of x is, right? We don't know what sine of x squared is, but we know what sine of x is, right? It's this thing right here. So yeah, don't forget your thing. I'll write it out. Please. I believe I'll just do it off memory. I believe it's x 2n plus 1 divided by 2n plus 1. Right? Factorial. I forgot the factorial. Yeah. Okay. Perfect. Okay, so, well, this one's easier than this one, right? Because it's already in the signed form, so all we have right now, all we have to do is replace it with this, right? So, our new x is x squared, so that's all we have to plug in, right? So that's easy enough. You should do it on your own, twin, so you know, you really have it simplified in that small p brain of yours. Plug it in, so that's going to be x squared, right? And then 2n plus 1 over 2n plus 1 factorial. And then, you could just leave it in this form, or you could, just probably, like, simplify it, I guess, right? So if you, I guess, what is it called, expanded? No, there's a math word, but I forgot. But now you do times 2n, that's x, wow, x 4n plus 2, that's a 2. And then this would be your answer. Answer. And then according to the chart, this is the interval convergence, so, and since we use it, it's going to be the same thing, so. Yep, and then this is going to be the series answer, and this is our interval convergence. So, yep, that's the answer. Easy peasy, twin. I think you could do it, twin. And then this is yeah, these were all Maclaurin series, right? This is Maclaurin series, which is when the center is A. Wow, when the center, which is A, equals 0, is what I meant. So Taylor series when it's not centered at 0. So in this case, A equals pi over 2, so that's going to be the new center, okay? So before you start tweaking out, breathe in, breathe out. Okay, we got this one, okay? So if you recall, this is the equation for a Taylor series right here. Right, so I'm going to rewrite that down here. So yeah, right here. So we're trying to look for this thing, or put it in these terms. Yep, so hopefully this looks familiar. It's basically the same thing as Maclaurin, but Maclaurin is just DNF, so it gets 0 points. Remember that. Okay, so, and we have this, right, but we can't use a previous one, right, because this is Maclaurin series, right, when we're looking for Taylor series. So we gotta start from the top and make our little graph, right? So this is going to be our graph. I'll just write, because it's A, right, but in this case we know what A is, so I'll just write it here. And then the form, right, and then x minus A, which is pi over 2, and over and factorial. Okay, start graph. Okay, straighter lines. Let's go. I'm so good at it. Okay. I think it's gonna have to be longer, fuck, because cosine x, right? Cosine sine, it's usually the 4. Yeah, this is way too short. Okay. Okay, so this is the thing, right? This is derivatives. Remember, this is first column derivatives, second column derivatives, plugging in A, and then the last one is plugging into the final thing that we're looking for, right? So when n equals 0 for the derivative, that's just the original. That's a different color. It's too late. Original function, so it's cosine x, right? N equals 1, that's first derivative, so 3, 2, 1. If you said negative sine x, you would be correct. Twin. Then we just keep going. This is, and then for cosine sine, stop at 4 because it repeats, right? So then go to the next column, which is when you plug in pi over 2. So I'm gonna draw the unit circle. Pi over 2 right here, remember? In this case, it's 0, 1. Remember cosine x, sine is 1, x, I mean y. I'm just lying to you all the time. So cosine pi over 2, 0. Okay, negative sine pi over 2. Oh, that's negative 1. Because 0, this will be 1, and this is 0. So wow. If you remember, if the third column equals 0, that means there's no value, so we can just straight ignore it. So we just draw a line there, right? We don't have to deal with this, right? Okay, so now we plug it into things. So this thing right here is the third column, so we have negative 1 on top, times x minus pi over 2 to the power of n, which in this case is 1 over 1 factorial. So we do this same thing over here. And then save, we do it again for 5. That would be negative 1 because it's alternating there. Right, so now we have this. We can find the series for it, and we just write it all out. So we have this. So we know negative 1, well, that's just negative, and then 1 factorial is just 1. So this top part, or this first term right here, just be this, right? Next one, plus x minus pi over 2 to the third power over 3 factorial minus negative x minus pi over 2 to the power over 5 factorial, and then plus whatever, right? So then we have to like come up with a series. So again, if you have no clue where to start, first start off if there's negatives, and there's negatives, so it is an alternating series, so we just write that out. And then we'll start with the numerator, right? So it's always going to have x minus pi over 2, right? So we can write that, and then the thing, the power is what's changing, right? So, well, here, I'll write it. This is n equals 0, and this is n equals 1, and then this is n equals 2, right? How are you going to get this one, right? So, since the first one is n equals 0, right, the power can't just be n, right? Because then we wouldn't get, that would just make the whole n minus pi over 2 disappear. So that's crossed off, right? Now we see it's increasing by like power of 2, right? It's like 1, 3, 5. So 2n, right? But it's not even, so we just plus 1, right? So if we plug in n equals 0, 2 times 0 plus 1, that's 1. So that's where we get this one right here. And then if we plug in n equals 1, 2 times 1 is 2, plus 1 is 3, and that's n. So yeah, it matches, right? So that's how we know that's there. And then now we do the denominator, right? So we know this is going to be a factorial. So like this factorial would be 1 factorial, right? And then it's the same pattern as the degree, 2n plus 1, right? It's 1, 1, 3, 3, 5, 5, right? So then we could just kind of like see that's the same thing. Factorial, right? And then this is our series. You could check it. Make sure you check it when it works. So this is our Taylor series, right? So that would be the answer for this with the blue. I don't know if that's confusing. I'll rewrite this. Oh, my music just stopped. that's awkward. We are now in silence. Okay. Close your eyes. I'm gonna restart that music. Okay. Okay. Whatever. So this is the series that we're looking for. Oh, it's not asking us for interval convergence. Okay, but in the case that it was, I'll just work it out so you know how to do it. So how do we look at this and we're thinking, okay, how do we how do we test for the convergence? Hopefully you said ratio test. Forgot what I was talking about for a second. So we use ratio test. Alright, yeah, you have a space right here. Right, so then it's the a sub n plus 1 over a sub n, right? So, and you can ignore the alternating factor. So this first term right here would be this 2 times n plus 1. So that's going to be 2n plus 2 plus 1. So 2n plus 3. Did I go too fast? So I'm just talking about this part. So it's going to be 2n plus 1 plus 1, right? So this is 2n plus 2 plus 1, so then 2n plus 3. Just in case you got confused, because I did kind of say that fast. I'm sorry to me. Okay, next one we have the bottom, which is going to be, again, like this right here. So 2n plus 3 factorial. And then we plug in the normal. Right, and then if you expand it, I have space. No, I have space. So this top one could also be rewritten as x minus pi over 2n times x minus pi over 2 to the third, right? Because this thing right here, and x, like, that's the rule. Bring this down. Alright, and then over here, x minus pi over 2 2n times x minus pi over 2 to the first power times, and then we expand this until we get what we want, which in this case is 2n plus 1 factorial. So then we cross out the terms. This crosses out that, this crosses out with this. So then we're left with x minus pi over 2 third, and then x power 2 first power, and then times 2n, 2n plus 3, 2n plus 2, right? So then if we do the ratio test with this, we can, well, first we take out the coefficients, right, which these two, right, these x, because x will always be the same, so we can take out this, and since it's to the third power over the first power, we can simplify that, right? So it's going to be x minus pi over 2 to the second power, right, and then we're just left with 2n plus 3 times 2n plus 2, approaching infinity, so that's going to be 1 over infinity, which is equals to 0, and then that's less than 1. So according to the ratio test, this will converge, and then if we're testing for like which x's or any exceptions, we look at this part right here, right? So x, whatever x is, doesn't matter because it's going to be multiplied 0, and then it's always going to be 0, meaning it's always going to be negative 1, which means it's always going to converge. So for all x, it converges. So that means radius of convergence is infinity because it's for all x, and then the interval of convergence is going to be negative infinity to infinity. This here is the that's kind of like the whole thing on screen. So this is radius convergence, and then this is the finding the Taylor series. Hope this helped, Twin. Let me know if you have any questions, Twin. And good luck, Twin.